All right, I hear the recording in progress. We'll share the screen. Okay, so we're up to 7.4. Continue on with 7.4. Okay, quiz tomorrow. Quiz will just be on 7.3 material. Okay, so I'll give you a couple of questions from 7.3. The trig substitutions, in particular for the quiz tomorrow. You are going to need that table, right? Page 486. This thing. Okay, so I'll give you a couple of problems. You pick the right one, right? Does my integral look like that, or like that, or like that? And this tells you the substitutions that you need. Okay. So as usual for quizzes, you have until 11:59 p.m. Friday night to do the quiz. Should be lots of time, and it's open everything. So it's not really shouldn't be thought of as a quiz. It's more like just an assignment, but quiz is shorter to write. QUIZ is easier than ASSINGMENT, but you know, it doesn't really fit the normal definition of quiz. You get to talk about it. You get to help each other out. You get to look up stuff. So yeah. Okay. So just 7.3. All right, so continue on 7.4. I might finish 7.4 today. If I don't, and I might fall a little behind. We're still okay. I still have a buffer day next Thursday. And again, we're aiming for next Friday, the 24th, for exam 2. Okay, so now that we've had one exam, you know the way all my exams work. You turn in all this stuff for homework. You must submit at least 70% of the homework. That's really a joke because I do a vast percentage of the problems anyway, as a lot of you know. Okay, all right. Let's see, trying to fix up my screen here best I can. All right, so let's continue on with partial fractions and where we were. Back to 7.4. I'm going to do 19 star, which is not the same as our 19, but it shows you how to do a lot of the problems there. So I'm calling it 19 star. It was in the last edition's book. Okay, integral of x squared plus 1 over x minus 3, x minus 2 squared. Okay. Let's see, the denominator is 3rd degree. The numerator is 2nd degree, so that's okay. If that's not the case, then what you would normally want to do is to do long division. Right? Do the polynomial long division until it's the way that you want it to be, but it is the way I want it to be. Now, x squared plus 1, treat it as x squared plus 0x plus 1. And there's a reason for that, as I'll show you a little bit later. Okay, so this kind of piggybacks off of what we said yesterday. I've got x minus 3, x minus 2 squared. So this is linear. This is a linear which is repeated. Therefore, the setup is x minus 3. And then what do I do for x minus 2 squared? X minus 2 and x minus 2 squared. Okay. Remember, if this was x minus 2 to the 5th, then you go x minus 2 squared, cubed, 4th, and 5th. Okay, and of course, I would never make you do anything that long. Okay, this is already pretty long in itself. It's just a messy algebra. So once I find a, b, and c, it's fairly easy to integrate. This is going to be an ln. This is going to be an ln. This is going to be power root. It'll be c times x minus 2 to the negative 2. Okay, temporarily ignore the 10, negative 9, and negative 5. That's what it comes out to be. Okay. So from here, I need to bring up the common denominator of x minus 3, x minus 2 squared. So that means this fraction needs x minus 2 squared. This fraction needs what? X minus 3 and x minus 2. And this fraction needs x minus 3, right? To get a common denominator. So they all have x minus 3, x minus 2 squared now, right? X minus 3, x minus 2 squared, x minus 3, x minus 2 squared. Okay, and then I have to multiply all that stuff out, right? So multiply all this stuff out. A times x minus 2 squared is x squared minus 4x plus 4. B times x minus 3, x minus 2, x squared minus 5x plus 6. C times x minus 3 over x minus 3, x minus 2 squared. Okay, just the usual getting a common denominator stuff. Okay, so back up here one more time. Okay, break up the original into x minus 3, x minus 2, x minus 2 squared. Right? That was case 2 from yesterday. Remember, we have a case 2. I can show you that quickly again. Case 2 on page 496. The quotient is a product of linear factors, some of which are repeated. Right? So here's an example. X squared, x squared. X minus 1 cubed, x minus 1, x minus 1 squared, x minus 1 cubed. Right? All right, now, again, trusting your ability to do the algebra, because it's going to be quite messy if I write it all out. There's going to be some x squared, there's going to be x and constant. So x squareds are these two, right? Ax squared plus bx squared. Look through this whole thing. There's an ax squared and bx squared. So there it is, a plus b x squared. How about x's? Here, here, and here, right? So it's negative 4a minus 5b plus c. That's my x. Okay? If I multiply it out, it's negative 4ax minus 5bx plus cx. Take out the x. Negative 4a minus 5b plus c. That says negative 4a minus 5b plus c. I'll raise it up maybe. Negative 4a minus 5b plus c. Okay? And now constants. Constants means there's no x. 4a, 6b, and a minus 3c. So there it is. So it's blah, 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 x squared plus blah, 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 x plus blah, 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 which doesn't have any x at all. Okay. And all of this has to equal 1x squared plus 0x plus 1. Right? Which means 1x squared, a plus b has to equal 1. Negative 4a plus, minus 5b plus c has to equal 0. And all this stuff has to equal 1. So I have 3 equations and 3 unknowns. Okay, so the coefficients of x squared have to match. Back up here. So a plus b equals 1. The coefficient of x is 0. So negative 4a minus 5b plus c is 0. And the constant has to be 1. So 4a plus 6b minus 3c is 1. So these three equations and 3 unknowns. Okay, so there's several ways to solve that. I decided to aim for substitution. If a plus b equals 1, that means b equals 1 minus a. And I plug that right into here and right here. So negative 4a minus 5b, which is parentheses 1 minus a, plus c equals 0. And clean this up. Negative 4a minus 5 plus 5a plus c equals 0. That gives me a plus c equals 5. A plus c, add 5 to both sides, a plus c equals 5. Okay, and now 4a plus 6b, b is 1 minus a, there it is, minus 3c equals 1, clean it up. 4a plus 6 minus 6a minus 3c equals 1, and that gives me negative 2a minus 3c equals a negative 5. Negative 2a minus 3c, subtract 6, I have that. So I have this equation and this equation, multiply both sides by 2. 2a plus 2c equals 10. Add them up, a's drop out. So I have negative c equals 5 or c equals negative 5. Then I start plugging back in. If c is negative 5, put it right there. That makes a equal to 10. And then I plug back in for b. B is 1 minus a. So b is 1 minus 10, which is negative 9. So if a is 10, b is negative 9, c is negative 5. So that's where I got these 3 back up here. So now I know my original integral, I can change to 10 over, easy natural log, minus 9 over, easy natural log, minus 5. And then I'm going to raise that up as x minus 2 to the negative 2. Here we go. So here's my original integral. 10 over x minus 3 minus 9 over x minus 2 minus 5 times x minus 2 to the negative 2 dx. Okay, so that's pretty much it. 10 ln absolute value of x minus 3 minus 9 natural log absolute value of x minus 2. This one's not a natural log. Just do the power root. Negative 5 x minus 2 to the negative 1 divided by negative 1 plus c. You don't have to worry about the chain root because the derivative of x minus 2 is 1. So I don't have to worry about multiplying by anything else. So we're good there. And a little bit of cleanup there. So 10 natural log absolute value of x minus 3 minus 9 ln absolute x minus 2. And this becomes positive 5 over x minus 2 plus c. And there we go for that one. Okay, the next one I was going to show you is 23. That is an assigned problem. (10 over x minus 1, x squared plus 9). All right, so from what we said yesterday, this is a linear expression. Aha, x squared plus 9, irreducible quadratic, right? So that's our case 3 from yesterday, page 497. So for instance, look at what they did for x squared plus 1. Above it, bx plus c. And likewise, x squared plus 4, dx plus e. So if you have an irreducible quadratic, that means you can't factor it. Then you need a linear expression on top, bx plus c. And the key item is irreducible. So again, if this is x squared minus 1, you wouldn't do this. You would just factor x squared minus 1 into x plus 1, x minus 1, right? So here, x squared plus 9. If this had been x squared minus 9, you wouldn't do what I'm about to do. You would just factor into what, x plus 3, x minus 3, and go from there, right? But because it's x squared plus 9, look at the way we have to set it up, right? X minus 1, a on top. X squared plus 9, but on top is a bx plus c, right? And again, temporarily ignored this. That's what the answer turns out to be. So a over x minus 1, bx plus c over x squared plus 9. This is my ln. This is going to be an inverse tangent thing. Okay. And for this one, 10. Pretend it's 0x squared plus 0x plus 10. The basic idea is if this is third degree, you need something second degree on top. Okay, so treat 10 as 0x squared plus 0x plus 10. All right, so I've got my a over x minus 1 plus bx plus c over x squared plus 9. So what do I need behind my 2 pens to get a common denominator, right? So what does this left-hand side need? X squared plus 9. And what does this right-hand side need? X minus 1. We know the way it works. So I have my common denominator. And this time I think it's too confusing to try to do it in your heads. So we'll just multiply it out. Ax squared plus 9a. This one just FOIL it out. Bx squared minus bx plus cx minus c. Now gather like terms. I know there's a lot of letters, but we're only focusing on x being the variable. So where are my x squareds? Here and here. A plus b parentheses x squared. And then my x's are here and here. Negative b plus cx. And then my constants, that means doesn't have any x, 9a minus c, 9a minus c. Right, quick double check, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right. I guess I could have done my double checking over here too, but anyway, we know it worked. Okay, so now this fraction has to equal 10 over x minus 1, x squared plus 9, or more strictly speaking, 0x squared plus 0x plus 10 over x minus 1, x squared plus 9. So how do I find a, b, and c so that this fraction matches this fraction? Okay, well, the bottoms already match. So how do I match the top? Behind my pen here better be 0. And behind my pen here also better be 0. And behind my pen here better be 10. Okay. So in other words, a plus b has to equal 0. Negative b plus c is also 0. And 9a minus c equals 10. So 3 equations, 3 unknowns. And that can be solved any number of ways. If I add directly, just add all 3 of them up. B's drop out, C's drop out, 10a equals 10, so a is 1. And it looks like a and b are opposites, so b is negative 1. And from this equation, c and b are the same, so c is also negative 1. So a is 1, b and c are negative 1, so it comes back up to this. So I have this. And I'll break this up into 1 over x minus 1 minus x over x squared plus 9 minus 1 over x squared plus 9. So I have 3 integrals. So I'll call them I1, I2, and I3. So the original integral is I1 minus I2 minus I3. Okay, so again, I will always stand for my original integral. And if I have to do an integral inside an integral, I'll call it I1, I2, I3, or whatever the case may be. Okay. All right, that looks like a simple ln. That looks like a substitution. That looks like an inverse tangent thing. All right, so I1 is pretty straightforward. It's ln absolute value of x minus 1 plus C1. Okay, again, right here, if I'm doing integrals within integrals, you can't just call them all plus C, because mathematically that implies that the C's are the same. They don't have to be the same. So this one I'm going to call a C1. There's going to be a C2 and a C3. But in the final answer, you've got C1, an arbitrary constant, plus or minus a C2, another arbitrary constant, plus or minus a C3. And all of that combined will just be C in the final answer. Okay, I2, x over x squared plus 9. Use substitution. The derivative of the bottom is 2x, which means I just need to introduce a 2.5 outside. So u equals x squared plus 9. Du equals 2x dx, u substitution. So put a 2 inside and a half outside. So now this combination 2x dx, pretend I erase it with du, and the bottom is just going to be my u. So I have 1/2 ln absolute value of u plus C2. Okay, change u back to x squared plus 9. And here's another important principle, and you should do this. And if you don't do this, I may take off points for this. How did I change that to parentheses? Well, there's absolute value. What do we know about absolute value of x squared plus 9? The sign, SIGN, always must be positive, right? Got to be positive. This class, there's no imaginaries, no square root of negatives and all that. X squared plus 9 has to be positive. Therefore, you should drop the bars. X squared plus 9. Now, if this had been x squared minus 9, we know that has a chance of being negative, then you have to leave the bars. But x squared plus 9 is dead sure positive. Change it back to parentheses. All right, I3, a little bit of work. Integral of 1 over x squared plus 9. Now, I know the integral of 1 over 1 plus x squared is my inverse tangent. There's a 9 in the way. The way to get around it is to factor out the 9. So 9 comes out. X squared over 9 plus 1. Okay. It's almost like, okay, if I take a 9 out of the x squared, I have to quickly divide by 9. Okay. You can convince yourself by multiplying this back out. What's that times that? X squared. What's that times that? 9. So it works. And I'll take out the 1/9, rewrite this as 1 over 1 plus x over 3 squared. I need to write it as some quantity squared in order to do my inverse tangent. Okay, so u equals 1/3 x, du equals 1/3 dx, which means I need a 1/3 inside and a 3 outside. So now 1/3 dx is my du, 3/9 is 1/3, and I have 1 plus u squared. So this is perfect for inverse tangent now. So I have 1/3 arctangent or inverse tangent of u plus c3. Change u back to what it was, 1/3 x or x/3. So 1/3 inverse tangent x/3 plus c3. Okay, and finally, put them all together. I is I1 minus I2 minus I3. So I1 was this, I2 was this, I3 was this. So here we go. ln absolute value of x minus 1, I1, minus I2, 1/2 ln x squared plus 9, minus I3, 1/3 inverse tangent x/3, and then plus C1 minus C2 minus C3. Now you can just put them all together. It's just plus C. Okay. Okay, 29. It's a little bit different. It's x plus 4 over x squared plus 2x plus 5. It's a little bit trickier. And let's see. I'm noticing it's actually not, actually wasn't on our original list. Okay, so I'm going to put it in. So I'm putting in 29. And I'm about to set it up for you anyway. Okay, let's see. 23 inverse tangent. I think if you mean over here, we know that the integral of 1/1 plus x squared is inverse tangent. Back at this stage, if that's what you mean, the derivative inverse tangent of u was 1/1 plus u squared. Therefore, the integral of 1/1 plus u squared is inverse tangent. Okay, and if you want to put that in your cheat sheet, you may. I think even at the beginning of this chapter, it's on our list. I guess I don't see it here after all. Yeah, I guess it's not here. Well, maybe it is. Well, there's a variation of it, that bottom one there, but I don't really like that one. It's going to take me a while to find it back in Calc 1, but anyway, this is it. The derivative inverse tangent was 1/1 plus u squared. Therefore, the integral of 1/1 plus u squared is inverse tangent. Okay, I'm not sure if that answers your question, but if not, you can ask again. Okay, 29. The way to do 29 is this. The game I'm playing is, I wish the bottom were x squared plus 2x plus 1, not plus 5. So I'll just make it x squared plus 2x plus 1, and then plus another 4. That factors this into x plus 1 squared, and the numerator, x plus 4, I'm going to write as x plus 1 plus 3. That way I'll do a substitution. See? So x squared plus 2x plus 1 factors in x plus 1 squared plus 4. Let t equal x plus 1. dt equals dx. So right here, change that to t, change that to t. So it's going to become t plus 3 over t squared plus 4. And then I'll just say, etc. You break it into two integrals. T over t squared plus 4. That's almost exactly like how we did I2 over here, substitution. And then 3 over t squared plus 4, inverse tangent. work that out like this one. Okay, so that's my hint for 29 star. I'm sorry, not 29 star, that is actually 29. Okay, then 39 to 43 are rationalizing substitutions. Okay, and the one that I'm doing isn't the same as any of these, but it gives you a similar thought there. Okay. So I'm going to show you 39 star. Integral of radical x plus 1 over x dx. Okay, so the game we play for this one is to say, well, I don't like the square root of all of that. How about I'll just call that t? Let t be square root of x plus 1, that whole thing. And then I can get the ball rolling. So t equals the square root of x plus 1. Now I square both sides. T squared equals x plus 1. Differentiate both sides. 2t dt equals dx. And x is equal to t squared minus 1. All right, so I do all that stuff. Look at what happens. I now have the integral of radical x plus 1, which I now know is t because I made it that way. Dx is 2t dt, all divided by x, which is t squared minus 1. Take out the 2, t squared over t squared minus 1 dt. And there it is. Now I know how to integrate that. I'm going to factor this. Okay, now this one I could do the long division if I wanted to, but I'll show you a trick that is often useful. See how the top and the bottom are almost the same? T squared minus 1. The trick is to go ahead and make them the same and then just compensate. In other words, on top, I'll just go ahead and put minus 1, so they'll cancel out. You say, well, that's not fair. It is fair if I immediately add 1. Okay. So let me show you how to do that. Let me see. So I go t squared minus 1, and then I quickly add 1. T squared minus 1 plus 1 over t squared minus 1. That way I can break it into 1, here's 1, plus 1 over t squared minus 1. Okay. In this instance, it's actually easier to bring the 2 back in, so I don't have to fool with it. So distribute the 2 back in. 2 plus 2 over t squared minus 1, which factors into t plus 1, t minus 1. So I'm going to call this I1. I'm going to call this I2. I1 is easy. It's the integral of 2. So it's the integral of 2t plus c1. I2 is 2 over t plus 1, t minus 1. So partial fractions, right? 2, I'll call it 0t plus 2. Again, the bottom is second degree. Therefore, the numerator needs to be first degree. 0t plus 2 is a over t plus 1 plus b over t minus 1. And again, temporarily ignore the negative 1 and 1, which is what they're going to become. But then we do the partial fraction stuff again. So a over t plus 1, b over t minus 1. Okay, so what does this left side need? T minus 1 over t minus 1. And what does this right-hand side need? T plus 1 over t plus 1. That way I have a common denominator. And now on top, I have at minus a plus bt plus b. Gather like terms, gather the t's together. Here are the t's. A plus bt plus parentheses negative a plus b. That's the constant term. It doesn't have any t. And it has to equal 0t plus 2, which means a plus b is 0. Negative a plus b equals 2. 2 equations and 2 unknowns. Add them up. 2b equals 2. B is 1. Therefore, a is negative 1. Right? This equation says A and B are opposites, right? A equals negative B. So B is 1, A is negative 1. So that's where that negative 1 and 1 come in from, right here. And I decided to write it with the B first, so it's positive and negative. So I write it as 1 over T minus 1 minus 1, that's a 1 there, over T plus 1. All right, so ln absolute T minus 1 minus ln absolute T plus 1 plus C2. Okay, and to just make it more compact, I can put them together like this. Right, remember in logs, yeah, log A minus log B is a log of the quotient, right? So ln T minus 1 over T plus 1 plus C2. All right, put them together. So I is equal to I1 plus I2. I1 was just 2T. And I2 was all this, ln T minus 1 over T plus 1 plus C1 plus C2 is C. Okay. And we're still not done. We had to substitute twice, actually. Way back at the original problem was in X. Okay. And we said T is equal to radical X plus 1. Way back over here. T is radical X plus 1. So change that, and that into radical X plus 1. And finally, I'm done. Okay, so 2 radical X plus 1, ln absolute value of radical X plus 1 minus 1 over radical X plus 1 plus C. Okay. So there we go with that. Okay, so that's how to do that problem, which is unfortunately not any of ours, but I can go ahead and tell you the key ideas here. It's almost like that weird radical, make it nice. Okay, so for 33, I would say let T be square root of X minus 1. So I'll go ahead and give you what the substitutions are. T equals radical X minus 1, and go from there. This one, T equals radical X. This one's a little tricky because there's a cube root there. Okay. So because of the cube root, I'm going to say T cubed equals X squared plus 1. So I haven't shown you how to do any of these in its entirety. That's a substitution we would make. T equals radical X minus 1. Right? That way you don't have to square root of X minus 1. You just call it T. And that one is T. And because of the cube root, I'm going to call everything behind my finger T cubed. And the reason why I want to do that is so that I can take the cube root of T cubed and I'll just end up with a T. Right? Okay, so this one you're going to square both sides, right? And here you're going to square both sides. And here, it's already good. You can just go with it. Okay. So substitute as necessary. It looks like for this one, you're going to go something like 3t squared equals 2x dx. So that should help you for 43 somewhat, hopefully. All right, I'm actually done with this section. Okay, so mark this off. I will introduce 7.7. And for 7.7, do not do any of the problems in the book. That's when we do all of this, which right now you don't even know what it means. But that's okay. I'll show you probably half of them and what to do. Okay, so 7.7 is an approximate integration. Let's see what that's about. What are we skipping? 7.5 is called strategy for integration. So it's kind of just a review. I decided not to do the review. So it just combines all the stuff. Oh, there's another table of integrations. Page 503. constants of integration have been omitted. So technically, we know it's supposed to be plus C. They got lazy and not put the plus C. But here's a whole table. Okay. And we have integral of tan. There's integral of cotan, integral of secant, integral of cosecant. Right? 7.6, integration using a table and computer algebra systems. Okay, that means just let your calculator do it or your computer do it. Well, this is not a computer course, so that's why I'm skipping that. Integration using a table. What are you missing? The back of the book, there's this whole big table of integrals. And it might take me a while to find it. Not sure if it's worth it now. So, yeah. Reference page 7 way in the back. Table of integrals. Okay. Number 1 looks like integration by parts, and then they give you, the basic power rule and ln and all that stuff. But they got some pretty exotic ones here, and there's a whole bunch there, and more there. So it looks like they got 112 integrals. Right, you just have to look up the right one. So I said, okay, we don't need to do that. So that's what we're so-called missing. All right, so 7.7, you are going to need a calculator, very calculator dependent. Approximate integration. There are still some integrals where it's impossible to find the exact value. There's some situations where it's impossible to find a definite integral. Sometimes it's difficult or impossible to find an antiderivative. Here are some which we cannot do. E to the x squared. You might think I can find an antiderivative that easily. No, you can't. I guarantee you can't. Okay. This one you can't find an antiderivative easily either. Radical 1 plus x cubed. We actually going to be tackling some of these types in our last chapter, but it's not done by normal means. We have to do something called series method, and I'll show you that when we get to it. So what are we going to do? We just do approximations. Remember doing stuff like this before? Left endpoint, right endpoint, midpoint. Okay, well, we're going to resurrect the midpoint method, okay, but we're going to do some other methods. Okay, so you're not going to do left endpoint and right endpoint like you did in Calc 1. You will do midpoint rule. It's on page 515. The midpoint rule that they have here is correct. I'm going to give you my version of it, which I think is easier. We're also going to learn something called the trapezoidal rule. Page 516. Yeah, what they have is correct, but I'm going to give you my version. And the third method is called Simpson's rule on page 519. Simpson's rule. Page 520 has the rule. Again, it's correct, but I think it's better if you use my version, which I will show you presently. All right, so let me get this down. Okay, 7.7, approximate integration. Okay, midpoint rule, trapezoidal rule, Simpson's rule. Underneath each of these, I tell you what shape that they're using for the approximation. Midpoint rule uses rectangles. Just like in Calc 1, when you did the left endpoints, the right endpoints, and the midpoints, they were all rectangles. The trapezoidal rule uses, big guess, trapezoids. Simpson's rule uses parabolas. And a key thing for Simpson's rule is that n has to be even. I haven't even defined what n is, okay, but n has to be even. There's a number of pieces that you chop up the subintegral into. Okay. here's what I think you should put in a cheat sheet. Now, what the text has is correct. It's more wordy. I've got it more compact. Okay. MN for midpoint rule, TN for trapezoidal rule, SN for Simpson's rule. Okay. Simpson was a mathematician many years past. Okay. Delta X over 1, delta X over 2, delta X over 3. Yeah, you might say, well, you don't have to write divided by 1. Yeah, but if you had to memorize it, which I made my previous class do when we were pre-pandemic, then I just say memorize 1, 2, 3. Easy as 1, 2, 3, right? So delta X over 1, delta X over 2, delta X over 3. Okay, midpoint root, they're all ones. 1, 1, 1, 1. You don't even know what this means yet, but just put it down. Trapezoidal root. 1 at the beginning, 1 at the end, and all the in-between ones get 2s. So 1, 2, 2, 2, 2, 2, 1. Simpson's root. And Simpson's root, n has to be even. Okay. Midpoint root, trapezoidal root, you don't have to have an even number. Simpson's root, you do need to have an even number. Okay. Now, if you look at the problems that we have, all the ends are even. So you don't have to worry about that. Okay. But technically, midpoint root and trapezoidal root, you could have odd numbers. Simpson's root, you're not allowed to. It must be even. But the ones I have, they're all even. Here's Simpson's root. 1 at the beginning, 1 at the end, just like the trapezoidal root. And then you alternate 4, 2, 4, 2, 4, 2, 4, 1. If you do it the right way, the second to the last one should also be a 4, and you finish with a 1. Okay, so I would say on your cheat sheet, put just this. Don't put what it says in the book. I think it's more compact this way. So MN, N is the number of pieces that you're chopping up the interval into. TN and SN, delta X over 1, 2, 3. Actually, the midpoint root, you already know it from Calc 1, right? They're all ones, 1, 1, 1, 1. Trapezoidal root, delta X over 2, 1 at the beginning, 1 at the end, and all the in-between get 2s. These are going to turn out to be coefficients. Okay. And Simpson's root, 1 at the beginning, 1 at the end, in between, alternate 4s and 2s, 4, 2, 4, 2, 4, and 4, and you end up with a 1. And just a little bit of theory as to what's going on. Midpoint root you've already seen. You break these pictures into rectangles. So for midpoint root, figure 1, page 515. You saw this before. You saw this before. Midpoint root. Approximate the area under the curve. Well, they chop the interval into 4 pieces. 1, 2, 3, 4. Take the midpoints. 1, 2, 3, 4. Go straight up, touch the curve. Straight up, touch the curve. Straight up, touch the curve. Okay, you get these 4 approximating rectangles. So we will approximate the area under the curve by the area under the rectangles. Trapezoidal root looks like this. Don't take the midpoints, just take the endpoints. Okay, and we say, what if I just go straight from there to there, and there to there, and there to there, and there to there? I have 1, 2, 3, 4 trapezoids. And you might recall in your 7th grade or 6th grade, there was actually a formula for the area of a trapezoid. It was 1/2 base 1 plus base 2 divided by 2. Okay. So you use a formula for this one, this one, this one, and this one. Okay. I can tell you a little bit of that. You would do this, 1/2 base 1 plus base 2 divided by 2. By the way, that's where the divided by 2 comes from. They're all going to be 1/2 base 1 base 2 divided by 2, right? So 1/2 that plus that divided by 2, 1/2 that plus that divided by 2, and all the way down the line. Well, you notice all the in-between ones get counted twice. See, base 1, base 2, base 1, base 2. Aha, this one get counted twice. Base 1, base 2, this got counted twice. Okay, the only ones that don't get counted twice are the very first one and the very last one, which is exactly the reason why the formula is delta X over 2, 1 at the beginning, 1 at the end, and all the in-between guys get 2. Because when I add up the areas of the trapezoids, this one gets counted twice, this one's counted twice, this one's counted twice, but the first and last one are only counted once. Okay. Finally, for Simpson's rule, the approximating graph are parabolas. Okay, so you take 1, 2, 3, 4, 5, take every 3 points, you have to have an even number. See how it has 6, right? Divided into 6 pieces, and you chop like that and like that. And what they do is that for these 3, you draw the best approximating parabola. That can always be done. If you take 3 random points, you can draw a parabola joining them, unless they form a straight line. Then you just draw the straight line. But imagine I have 1 point here, 1 point here, 1 point here. There's a parabola that joins them. Same thing here. There, there, there. Draw the best approximating parabola. There, there, there. Draw the best approximating parabola. So we replace the graph with an approximating parabola under Simpson's rule. If you do the heavy-duty math, this is what it comes out to be. Okay, so the midpoint rule uses rectangles. Trapezoidal rule uses, big surprise, trapezoids. Simpson's rule uses parabolas. Okay. Simpson's rule usually turns out to be the best approximation because it's a curve. Okay. Most of the stuff that we're doing are curves, right? The curve. Midpoint rule, you're using rectangles, those aren't curves. Trapezoidal rule, you're using trapezoids, those aren't curves. But the Simpson's rule, you replace it with a curve. And we know how to integrate parabolas. They're like ax squared plus bx plus c, right? So they can certainly be done. So the Simpson's rule generally turns out to be the best. And tomorrow I'll start showing you how to do some of that, but we're out of time for today. Okay, so tomorrow I'll get started on some of the problems in 7.7. Okay, but I want to leave you some time to start working on the quiz. Quiz will only be on 7.3 material. You have to pick the correct trig substitution for the quiz tomorrow. And it's due at 11:59 p.m. tomorrow evening. All right, so let me stop the share. And is there anything else in the chat? Anybody else with a question? All right, I don't see anything. All right, so that'll do it for today, folks. So everybody have a good day and see you next time. Okay, bye, everybody.